Okay, so far we've seen two theories for failure for ductile materials. We had the maximum shear stress theory. Then we had talked about distortion injury theory, which solved a problem. This theory, Coulomb-Mohr theory for ductile materials, is only when the ductile material has different yield strength in tension and compression. So Sy is different in tension than compression. So we'll call those, instead of saying Sy, we'll just use St for tension, the yield strength in tension, and Sc to be yield strength in compression. So this is for ductile materials which have different behaviors in tension versus compression. So theories in the past did not look at materials if they had different tensile stresses, or sorry, stresses in tension and compression. So let's assume that Sc and St are yield strengths in compression and tension respectively. What it means is that in that specimen I drew some time back, if you would load it with tension or you load it with compression till failure, and you'll see that Sc is not equal to St. Okay, but so what we find normally is that Sc is greater than St for most materials. In other words, the particular material can bear more compression than tension. So a simple way of considering this is to draw the Mohr circle for both those cases. So just like I drew a second back, I'll draw Mohr circle for both these cases. St, that's positive. So it's on the right-hand side of that sigma plane. And then Sc is, let's say, further down because Sc is greater than St. Okay, by that I mean the magnitude. So we can draw Mohr circle for this because 0 is the stress in the y direction. So the 0 is one of the points. And then we can draw another circle for the pure compression case. So what we have now is an envelope. So if you take a line and draw it such that it just touches the two circles, then the area between those lines is the area which is considered safe. This area. Failure envelope. This is the safe region. Okay, so what I did was there is a derivation on computing that safe region or those lines, which or the red lines, which basically gives you the safe region. And instead of deriving it, take me like 20 minutes. I'm just going to go through it quickly. I already shared those notes in the handout section. Okay, so that's basically the same. So the two circles, so there's a lot of things going on here, but this circle on the left and the circle on the right are the circles I drew previously. And we are trying to understand if a random loading condition lead to failure or not. So when you have a random loading condition, we can draw another Mohr circle. So this is the Mohr circle for the loading condition. Random load. Okay. So the way this goes is you pretty much have to use, well, first of all, you can compute the radius of each of these circles because you kind of know the 2 points on the diameter, right? You know SC and it's 0 over here and 0 and ST for that. So you pretty much know R1 and R3, and R2 comes from the fact that it is sigma 1, the maximum stress, minus sigma 3 divided by 2. And once you get the centers, that's this. Once you get the radius, then you can make arguments about similar triangles. So this triangle is similar to this triangle, which is similar to the longer triangle. So basically you can, once triangles are similar, you can take the ratios of their similar sides, and then you can use that ratio to compute an expression for those envelopes. So that derivation is here. I don't want to spend time on going on this. But what comes out of that whole derivation is this equation. It's very simple. Sigma 1 divided by ST minus sigma 3 divided by SC equals 1. So this equation is the equation for predicting if the material will fail or not. If this thing on the left side is greater than 1, it will fail. If it is equal to 1, it's just on the envelope, and to be safe, you want that to be less than 1. This is the failure equation. Like, remember we did this, sigma, like tau max equals sy divided by 2, sigma prime equals sy. So this is for the MSS, this is D. So we have these expressions for those theories. This is a similar expression for DCM, or Ductile Coulomb-Mohr Theory. Okay, so I'll post this derivation, but I don't think it's very essential, so I just don't want to spend time deriving things. However, what is interesting is we want to understand the failure region, just like we had the failure region for the first, the MSS and DSS. There was the ellipse and there was that hexagon. Similarly, we can find the area under in a 2D loading case based on this equation. So I'll do that. That's, I think, is very interesting. So let's see what this equation predicts on the failure region. So we have sigma 1 divided by ST minus sigma 3 divided by SC equals 1. Okay, so remember that sigma 1 is the maximum non-principal stress, sigma 3 is the minimum principal stress. The way we get this is once we have the element and we have sigma x, sigma y, tau xy, you can find sigma A, sigma B, sigma A and sigma B. Sigma C is obviously 0, it's plane stress. And then based on the magnitudes of sigma A and sigma B, you can make a call on what sigma 1, sigma 3 are going to be. So we pretty much get a few cases there. So sigma A is greater than 0, sigma B is greater than 0, and then the third stress, as I said, is always 0 because it's plane stress. Okay, so in this case, sigma A is, let's say the sigma 1 is sigma A. It could be sigma B, but that's not really, that's fine. Sigma 1 equals sigma A. And sigma 3 is 0, right? Because the minimum strain in this case is sigma C, which is sigma C. Okay, so what we need to do is once we identify the maximum stress and the minimum stress, we need to put that in the equation. So substitute in 1, we have sigma 1 divided by ST minus 0 equals 1, which means that the equation is S sigma 1 equals sigma A equals ST. Okay, so this is how you'll pretty much solve a problem, which is you'll identify the stresses which the sigma 1 and sigma 3 based on sigma A, sigma B, and sigma C. The second case is when sigma A is greater than 0, which is greater than sigma B, or one stress is negative. Clearly, one of the maximum stress is sigma A, and then sigma C is obviously 0. Sigma 1 is sigma A, and sigma 3 now is going to be sigma B. And the reason is because sigma B is negative, and so it's the minimum stress. Okay, so we can put that in equation 1, substitute in sub in 1. So we see that sigma A divided by ST minus sigma B divided by SC equals 1. And then we just have one more case corresponding to both these stresses being negative. So 0 is greater than sigma A is greater than sigma B. And sigma C is obviously 0. So here we would have the maximum stress is going to be 0. That is going to be sigma C. And the minimum stress is going to be sigma B. So we have sub in 1, we can write 0. So just put 0 for sigma 1 and sigma minus sigma 3, or sigma 3 sigma B equals 1, which means sigma B equals minus. Yeah. Sigma C. So those are my 3 equations, which I can now plot on the sigma A, sigma B plane to get that region which I got for D and MSS. Okay, so let's plot that. From 1 to and 3. Sigma A, sigma B. This will be case number 1. Okay, then we have from 3, we have S, I think it was sigma B equals minus SC. So that is in the negative region. So that would be somewhere here. This will be from 3. And then the middle case is this equation, sigma A divided by SC minus sigma B divided by SC. And that is an equation of a straight line with a slope of 1. So that would basically join these 2 points. This looks very similar to the MSS, except that those regions, it's a hexagon, but doesn't have the same sides, same length for the sides. In the positive, and so the first and the third quadrant. Two. Safe region. As long as your stress is in that region, you're considered safe. So this is how you can predict if the material is going to fail under any loading for a material which has different properties in tension and compression. If you want this to design using DCM for design, you need to incorporate a factor of safety. So the modification you do is you just divide ST and SC by N, right? Your actual stress, which is available to you, is 1/n of ST. So ST is, there's no factor of safety, but if there's a factor of safety, you want the maximum yield strength to be lower than the ST by a factor of N, and that's what I put there. Sigma 3 divided by SC equals 1. And if you simplify this, you get sigma 1 divided by ST, sigma 3 divided by SC, 1 divided by N. So that's your design equation. This is basically this region where we have sigma 1 should be, so here, sigma 1 is less than ST, or sigma A is less than ST, and sigma B is less than ST, right? This is the one for ST. Sigma B is less than ST, and this is sigma A is less than ST. So that is just telling you if something will fail or not. Now, so that is assuming that the element is done, is built, and you're predicting failure or not for a given loading. This equation is telling you that if I give you a loading, then what would be the factor, and it doesn't fail, what would be the factor of safety? What is the margin beyond which the stresses will actually cause it to break? That's one way of posing it. The other way of posing is, for a given kind of loading, how can you design this material? How can you design the dimensions of the shaft? So what you'll do is, I'll be giving you n, ST and SC is given to you, and then sigma 1 and sigma 3 are found from those equations, and they go back in your maybe a torque specimen or a bending specimen and give you the dimension. So this is just ensuring that your stresses sigma 1 and sigma 3 never really reach ST and SC. So they will be lowered by a factor n. So it keeps the design safe, because equal to 1 is when things will be on the verge of breaking if this theory is true. Does that make sense? And we have these same equations for other, for MSS and D, and it might just be best to show them right now as you guys are thinking about this. So these are the design equations for MSS, and MSS is down and D is up, which is just saying that normally sigma prime will be SY for verge of failing, but by keeping sigma prime lower than SY by a factor of n, or in other words, sigma prime is SY divided by n. Okay, so the first condition I wrote down is failure, right? If it's equal to or greater, it will fail. But by having it such that SY is divided by n, where n is greater than 1, we are ensuring that that sigma prime is a factor of maybe a magnitude or half, n is say 2, then it's half of SY. And so it'll always be, if you design it this way, it'll always be less than SY. And just giving you a margin of safety. So similar equations are there for that, and you just use those for design. Okay, so you can, we've only talked about how to use this theory for tension and compression, but you know, we might have a case where the specimen is subjected to shear. So how can you use this theory for shear? It's not that hard. If you have a pure shear, so using DCM for pure shear. So when I think of shear, just like I'm thinking of compression tension, I'm thinking about just shear like so, right? So that's pure shear. Again, I can draw the Mohr circle for this. Okay, so how will you start with the Mohr circle? Sigma x and sigma y are 0. So the way you do this is, so sigma x equals sigma y equals 0, tau xy is tau. Okay, so what you will do is, just like you would do any Mohr circle problem, we have 0, which is sigma x. That's going to be tau. And since our convention is counterclockwise positive, my bad, this should be, if you say this is phase A, this is phase B, this would be A, this would be, right? The convention is counterclockwise is negative, and that's why this will be phase A. And then clockwise is positive, that will be B. And then you just draw circle. And it's kind of obvious that this coordinate and this coordinate is going to be tau minus tau, because the radius is tau. So clearly this is sigma 1, maximum stress. This is sigma 3, right? The intermediate stress is 0 because it's a plane stress, so one of the stress has to be 0. So for pure shear, sigma 1 is tau, sigma 3 is minus tau, and so from DCM, we have sigma 1 divided by ST, sigma 3 divided by SC equals 1. So sigma 1 is tau, sigma 3 is minus tau, SC is 1. So if you do some manipulation, then you'll get this formula. Okay, so that's the value for tau for pure shear. You can compute the stress at which the element will fail in pure shear. Now, usually what we do is, just like there's an S is used to denote yield strength in tension and yield strength in compression, we can come up with another measure, let's say S, I've called it SY. This is the yield strength in shear, which is say, so the yield strength in shear is when things will fail, and so we can put SSY as tau. So here it is tau. SSY is STSC. When yielding. This is an equivalent value for shear strength in terms of ST and SC. And the reason why you do this is because it's actually pretty hard to make a machine element, a test specimen to fail in shear. So we never really have experiment where we are testing something in shear. Tension experiments are the most common one. It's pretty easy to create a tension specimen by using an Instron machine. Compression's a little bit more harder because when you do compress things, if you're not very careful about the length and the way you compress it, things can buckle. And buckling failure is a different failure from compressive failure. Compressing is literally when it crushes inside. Well, buckling is when it bends. You don't want bending when you're compressing. So those setups are more common, but shear setup is not there. And so you can use this formula to find the yield strength in shear if you know the yield strength in tension and yield strength in compression. Okay, so let's see if we can apply what we have here for DCM on a problem. Here's the problem. Should be on blackboard. Okay. Okay, so a 25 mm diameter shaft is statically torqued to 230 Newton meters, made of cast 195 T6 aluminum with a yield strength in tension of 160 MPa and a yield strength in compression of 170 MPa. It is machined to a final diameter. Estimate the factor of safety of the shaft. Okay, so we're given the diameter. It's 25 And then we're given the torque, 230 Newton meter. We're given the strength in tension. This is the yield strength. So that's 160 MPa. And then we're given the yield strength in compression, which is 170 MPa. And we are asked to find the factor of safety. Yes, I'm assuming that the setup is something like this, where the shaft is held in one side and then it's torqued. And then we keep increasing the torque to a value of 230 Newton meter. And assuming that's the maximum torque which is put on the applied to the machine element, we need to predict, well, it will not fail obviously because there's a factor of safety there. So we need to find what's the factor of safety. In other words, how far are we from failure? So if you increase the torque beyond that point to by a factor of NT, you should expect it to fail. Okay, so since we are given the SG and SC, this is you need to apply the DCM, right? MSS is ruled out and distortion is ruled out because they are for materials which have similar behavior in tension and compression. So the formula is sigma 1 divided by ST minus sigma 3 divided by SC equals 1 divided by N. So in that formula, ST and SC are known, N is asked. So we need to compute sigma 1 and sigma 3, and we would have figured out what N is, which is the factor of safety. Okay, so we have to here look at what's the stress in when a shaft is torqued. So when a shaft is torqued, we have a shear stress given by it's TR divided by J or T rho divided by J, right? So rho is the radius from, it's some radius. It doesn't have to be the diameter. So if you want to figure out where the maximum stress occurs, it will be on the outer surface of the shaft, right? When you put rho equals the radius, we would have tau equals maximum because tau is proportional to rho if T and J are fixed. So max tau max equals T divided by J. And now since we need to put the radius, and since we're given the diameter, I'm just going to use D divided by 2, which is the radius. Okay, so let's compute this. Torque is well, let me just put it in terms of variables first. So Tj is, this is I believe in the appendix A15, you have formulas for polar moment of inertia. J is pi e raised to 4 divided by 16, I think. Yeah, 32 for polar right side, and beam I is 60, 32. Then T divided by 2. So that is 16 T. In other words, tau max equals 16 T. Okay, so there we are, 16 times 230 divided by pi times diameter, which is 25 millimeters. So 25 millimeters is divided by 1,000 to get centimeters. So 0.025. Comes out to be 75 MPa. Yeah, so from this, we need to compute sigma 1 and sigma 3. Right? Sigma 1, sigma 3, which go in that equation which we are after. Okay, let's compute sigma 1 and sigma 3 now. Okay, so let's understand what's going on. So we have a circular specimen which is subjected to a torque. And so if you look at a plane element here, this is under pure shear. So because of the torque here, this is going to be under a shear stress, right? But then that shear stress cannot be by itself. There's a complementary stress which develops. So there would be stresses as shown. Okay, so I can redraw this in slightly better way, which what we're used to. Let's redraw this. And then this stress is max. Because it occurs on the outer radius of the cylinder. That's tau max. This is tau max. All of them are tau max. Okay, so this is where once we have the plane stress element, then we go back to resort to Mohr circle to find sigma 1 and sigma 3. Okay, so we've done this just a while back. We know the stress at phase A and phase B. So stress at A is well, it's 0 for the normal stress, and it is, so we have counterclockwise shear stress. So the sign for that is negative for our convention. So let's just put it here. That'll be minus tau max. This will be phase A. For phase B, we have 0 for the stress in the y direction. And then the shear stress on phase B is clockwise. The convention is clockwise is positive. That would be plus tau max, which is our phase B. We only need 2 points to draw the Mohr circle because they're on the diameter. So we can draw the Mohr circle. In this case, this point is sigma A. This point is sigma B. So you can see that sigma A is the radius, it's tau max. Sigma B is minus tau max. The stresses are sigma A equals tau max, sigma B equals minus tau max, and sigma C is 0 because it's a plane stress scenario. So now sigma 1 should be greater than sigma 2, should be greater than sigma 3. We need to arrange them in descending order. So sigma 1 is clearly sigma A. Sigma 2 is sigma C. And sigma 3 is sigma B. So sigma 1 is sigma A. And sigma 3 is sigma B. Which means that sigma 1 is tau max. Sigma 3 is minus tau max. Okay, so we've computed sigma 1 and sigma 3 now because we know what tau max is, in just a matter of putting it in the equation now. Yeah. We can use that too. So what we can do is, one option is what I did. Other option is you can find SSY. So compute SSY. And then use this formula. It's going to be SSY divided by tau max. It'll give you the same answer. So this will give you the same answer, which I'm going to compute in just a minute. Yeah, so if you do that, then you already worked out the math behind all this Mohr circle. It's already taken care of. Okay, so let's solve this. Just one more step left. So equation is sigma 1 divided by ST minus sigma 3 divided by SC equals 1. Sorry, 1 divided by N. So sigma 1 is tau max. ST is given. Sigma 3 is minus tau max divided by SC. I'm just substituting the values. So 75. ST is 160 plus 75 divided by 170. So N comes out to 1.1. Okay, which is saying that it's just it's on the verge of, I mean, if the factor of safety was less than 1, that means that that element will fail, because it's just saying that the stress is going to be more than the yield strength. But 1.1 is fine. You normally don't have something which is 1.1. You keep a factor, you keep like 2 or something like that. 2 is for lightweight structures like aircraft, where you're transporting things, much higher for ground vehicles and much higher for bridges and elements which are on the ground like buildings. Okay, we have 3 more minutes. One last thing before we stop for today. So we talked about 3 theories, right? We talked about MSS, DE, and DCM, which is the Ductile Coulomb-Mohr. So these theories are based on experiments and experience, right? So what we can do is we can take specimens in simple tension tests and load them to failure. And we do it for different materials, like some of the materials are shown here. And then we try to plot that stress on the sigma 1, sigma 2 plane. This is also sigma A, sigma B. And just to make it so that each of these materials have different SC and SC, so they're just non-dimensionalized by SC and S. Yeah, SC. Okay, SC, I think SC is the same as SY. Okay, so then what you do is you make these plots and then you can plot the contours for MSS and D, right? It is MSS, D. And what you notice is that a lot of these points actually lie on the DE, on the DE contours. Okay. This point is sort of inside, so it's good, it's encompassed. So just saying that the distortion energy theory is a better predictor for failure for those materials which lie on that curve. Okay? So D is better than MSS. In fact, MS is kind of more conservative. If you design based on MSS, it's not going to fail for sure because MSS is more conservative than D. So while the distortion energy is much more representative of failure, you might really want to design based on MSS because it's more conservative. What that will do is it will make the structure heavier because now you are using a conservative criteria to design the material. So that's kind of the evidence behind using one of the theory. Once you see this, you can make a judgment to design it. Some people might use MSS, some people might use D. It just depends on your application.